There is a specific kind of moment in science when the thing you are looking at stops making sense. Not in a frustrating way, not in the way that a broken piece of equipment doesn't make sense. It stops making sense in the way that a door you have walked through 1,000 times suddenly opens onto an entirely different hallway. Everything behind you is exactly as you remember it. But what you're looking at now, what lies on the other side of that door, is something else entirely. Something that doesn't fit the frame of reference you have been using your whole life. That moment happened on the morning of October 20th, 2017, in a data center connected to a telescope sitting near the summit of Haleakala, a dormant volcano that rises more than 10,000 feet above the Pacific Ocean, on the island of Maui, Hawaii. A Canadian postdoctoral researcher named Robert Werrick was doing what researchers at the University of Hawaii's Institute for Astronomy do on many ordinary mornings, reviewing the previous night's data from the Pan-STARRS telescope. Pan-STARRS, short for Panoramic Survey Telescope and Rapid Response System, is a remarkable piece of machinery. It is, in practice, an asteroid hunting machine. A 1.8-metre telescope fitted with a camera containing 1.4 billion individual pixels, which spends its nights sweeping enormous swaths of sky and comparing each night's images against previous nights to flag anything that has moved. Its primary mission is to catalogue potentially dangerous asteroids and comets that might one day threaten Earth. It is methodical, relentless work, the cosmic equivalent of watching a time-lapse of the night sky and looking for anything that twitches. What it captured on the night of October 19th, 2017, was something considerably more strange than an asteroid. In a 45-second exposure taken during the telescope's regular survey of the sky, there was a streak, a faint smear of light moving across the frame at a rate that was, to put it politely, unusual. The software that processes Pan-STARRS images initially rejected the detection multiple times. The object's motion was so extreme that the automated system couldn't fit it into any of the standard categories it used to classify solar system objects, and kept flagging it as a likely artifact, a glitch, something to be discarded. It took a human eye, Werrick's eye, to recognize that the streak was real, and that the motion it implied was genuinely extraordinary. The object was already hauling away from Earth at the time of that image. It had already passed the Sun, already swung through the inner solar system in a blazing arc that brought it within 37 million kilometers of our star, closer than Mercury, and had already started heading back outward toward the deep dark of interstellar space. By the time Werrick compared that October 19th image to a pre-discovery image from the Catalina Sky survey captured several days earlier, the object's motion pattern was crystallizing into something that had no precedent in the astronomical record. It was moving in a way that nothing born in our solar system moves. By October 22nd, just 3 days after the discovery observation, two facts had become undeniable. The object was on a hyperbolic trajectory, and it had arrived from interstellar space. Let me explain what hyperbolic means and why it matters so profoundly. Practically everything in our solar system, all 8 planets, all the moons, the millions of asteroids in the belt between Mars and Jupiter, the comets that make their long looping journeys from the Kuiper Belt and the Oort cloud, travels on what astronomers call elliptical orbits. An ellipse is a closed curve, like a stretched circle, and objects on elliptical orbits come back. They make their swing around the Sun and eventually return. Over years, decades, centuries, millions of years. They keep returning because they are gravitationally bound to the Sun. The Sun owns them. A comet from the distant Oort cloud might take 1,000,000 years to complete a single orbit, but it is still, in the most fundamental sense, a member of the solar system. It belongs here. A hyperbolic trajectory is different in kind, not just degree. A hyperbola is an open curve, like an ellipse that has been stretched to the point where it never closes. An object on a hyperbolic orbit comes toward the Sun, passes it, and then continues outward forever, its speed never dropping low enough for gravity to pull it back. The Sun cannot hold it. It is a visitor, not a resident. The mathematical measure of how hyperbolic an orbit is called eccentricity. For a perfect circle, eccentricity is 0. For an ellipse, it ranges from 0 to just below 1. Exactly 1 is called a parabolic orbit, the limiting case where an object is travelling at precisely the speed needed to escape the Sun's gravity, with nothing to spare. Above 1 is hyperbolic. Comets occasionally acquire eccentricities very slightly above 1, when they are nudged by gravitational interactions with outer solar system planets. They arrive on a bound orbit and leave on a marginally unbound one. But very slightly above one means values like 1.001 or 1.003. The eccentricity of this new object came out at 1.188. That is not slightly above 1. That is dramatically, emphatically, unambiguously above 1 in a way that cannot be explained by any interaction within our solar system. No planet, no combination of planets, could have accelerated a bound solar system object to this kind of speed. This thing had arrived with its hyperbolic trajectory fully formed, carrying a velocity that was far above the Sun's escape velocity, long before it ever got close enough for any planet to influence it significantly. It had come from somewhere else. It had arrived from interstellar space, from the void between the stars, from a trajectory that pointed back toward a distant region of our galaxy. For the first time in recorded human history, we were looking at something that was indisputably not from our solar system. The reaction within the astronomical community was immediate, electric, and global. Within hours of confirmation, observatories across the world were being redirected. Telescope time, always precious, always oversubscribed, was reshuffled and reallocated. Scientists were emailing each other at all hours. ESO's Very Large Telescope in Chile, one of the most powerful optical telescopes on Earth, was retargeted. The Gemini North Telescope in Hawaii was tasked. NASA's Hubble Space Telescope was scheduled. The Spitzer Space Telescope, an infrared observatory in Earth-trailing orbit, was added to the effort. For 2 months, this faint, fast-receding point of light received the concentrated attention of the best astronomical instruments in existence. The object needed a name. Before the official name was settled, there was some discussion of calling it Rama, after the enormous cylindrical alien spacecraft in Arthur C. Clarke's 1973 science fiction novel Rendezvous with Rama, which arrives in our solar system on a hyperbolic trajectory and baffles every human attempt to understand it. The parallel was irresistible enough to be mentioned openly in scientific discussions. But the Discovery team, working at a Hawaiian telescope on a Hawaiian volcano, chose to honor the language and culture of the islands. They consulted with Kayu Kimura and Larry Kimura, Hawaiian language experts at the University of Hawaii at Hilo, and the name they arrived at was Oumuamua. The name is written with a special character at the beginning, the okina, a mark representing a glottal stop in Hawaiian, which looks like an apostrophe but is its own distinct symbol. The pronunciation is O-mu-a-mu-a, with gentle emphasis on each syllable. It comes from the Hawaiian words au, meaning to reach out, and mua, which means first or at the vanguard, with the repetition adding emphasis, so the full construction conveys something like the first distant messenger reaching out ahead. The International Astronomical Union officially designated it 1I/2017 U1, with the I standing for interstellar. This designation was genuinely new. The IAU had never needed an interstellar category before. Our solar system had been catalogued continuously for centuries, and every object we had ever found, every planet, every asteroid, every comet, every moon, had been, in one way or another, native, born here or at minimum gravitationally bound here. The I designation had to be invented to accommodate this new reality, and that, in some ways, is the most significant thing about Oumuamua, not the specific details of what it looked like or what it was doing, but the simple fact of its existence as a confirmed interstellar object. It proved that objects from other star systems do pass through our solar system. It demonstrated that the instruments we had built were capable of catching them. And it set in motion a cascade of consequences. New missions, new survey strategies, new research programs, new debates that are still unfolding today. The mystery at its centre, what exactly was Oumuamua, and why did it behave so strangely, is the question that will occupy us for the rest of this video. But the existence of the question itself changed science. To understand why Oumuamua was so genuinely shocking, and why we had never found anything like it before, we need to step back and think about the long history of how humanity has watched the sky, what we were looking for, and what our tools were capable of finding. Human beings have been cataloguing celestial objects for as long as we have written records, and probably much longer. The ancient Babylonians kept detailed astronomical diaries, clay tablets recording the positions of the moon, the planets, and notable phenomena like eclipses and comets, that stretch back more than 2,500 years. ancient Egyptian temples were oriented to the rising and setting of significant stars. Polynesian navigators read the night sky with a precision that allowed them to cross the vast Pacific Ocean without instruments other than their own eyes and memories. The systematic quantitative study of celestial motion that we recognize as the ancestor of modern astronomy emerged in ancient Greece, was refined by Islamic scholars during Europe's medieval period, and then launched into its modern form by figures like Tycho Brahe, Johannes Kepler, and Galileo Galilei in the 16th and 17th centuries. For most of this history, the objects being watched were the same objects, generation after generation. The sun, the moon, the 5 planets visible to the naked eye, the occasional spectacular comet that lit up the sky for weeks or months before fading. The background stars were treated as fixed, an unchanging reference frame against which the wanderings of the planets could be measured. The concept that space between the stars contained objects that moved, that there was a population of dark, small, fast-moving bodies passing through the solar system on timescales too short for naked-eye observation, was simply not within the conceptual toolkit of early astronomers. The invention of the telescope in the early 17th century opened new categories of observation. Galileo saw moons around Jupiter. Giovanni Cassini measured the rotation periods of planets. Edmund Halley connected a series of historically observed comets into the single, recurring object we now call Halley's Comet. By the 18th and 19th centuries, systematic sky surveys were revealing that space was full of smaller objects, asteroids, discovered beginning in 1801 with Ceres, followed by hundreds more in the following decades. By the early 20th century, the catalogue of solar system objects had grown enormously, but the nature of that catalogue was still essentially the same. Everything in it was bound to the Sun, a permanent or at least very long-term resident of the solar system. The idea that debris from other star systems should be passing through our solar system occasionally is not new. Astronomers have known for decades that planet formation is an inherently wasteful, violent process that generates enormous quantities of ejected material. When a young star forms from a collapsing cloud of gas and dust, most of that material ends up in the star. Some of it forms a rotating disk around the young star, the protoplanetary disk, from which planets, moons, asteroids and comets eventually condense. But not all the disk material ends up in stable orbits. Early planetary migration, the way young giant planets shift inward and outward in the disk as they grow, disrupts the orbits of smaller objects throughout the system. A significant fraction of the original planetesimal population gets flung on increasingly eccentric orbits until they either fall into the Sun, get absorbed by a planet, or acquire enough velocity to escape the system entirely. This process in our own solar system is well studied, at least in broad strokes. The orbital architecture of the outer solar system, the way Uranus and Neptune ended up far from the Sun, the reason the Kuiper belt has its particular structure, the origin of the Oort cloud, all trace back to a period of dynamical upheaval in the early solar system when Jupiter and Saturn were migrating and everything else was getting thrown around. Simulations of this period suggest that our solar system ejected somewhere between 10 and 100 Earth masses of material. Some of it was captured in the loosely bound reservoir of the Oort cloud. Much of it was expelled entirely, becoming interstellar. And the same thing happened around every other star with planets. The galaxy contains between 200 and 400 billion stars. The Kepler Space Telescope, which spent almost a decade continuously staring at a field of stars and measuring the tiny dimming that occurs when a planet passes in front of its host star, determined that planets are extraordinarily common. Most stars have planets. Many planetary systems are architecturally quite different from ours, with giant planets in orbits very different from Jupiter and Saturn, which likely means ejection efficiencies and ejection compositions quite different from ours as well. But every star with planets probably went through some version of the chaotic early clearing out process. Multiply the expected ejected mass per star by the number of stars in the galaxy, and you arrive at a number so staggeringly large that it becomes essentially meaningless to express in conventional terms. The interstellar medium is not empty. It is swimming in planetary debris. The mathematical prediction that some of this debris should pass through our solar system was made explicitly by multiple researchers before Oumuamua was discovered. The numbers were uncertain by orders of magnitude. Estimating the density of interstellar objects before you have actually found one is like estimating the number of fish in the ocean by reasoning about how many fish should theoretically exist, but the consensus was that interstellar objects passing through the inner solar system should be a measurable phenomenon, and that survey telescopes of sufficient power should eventually catch one. The key phrase is of sufficient power, and for most of astronomical history, no telescope was sufficient for this task. Finding a small, dark, fast-moving object against the static background of stars requires a telescope that can sweep enormous areas of sky quickly, reach down to very faint objects, repeat its observations frequently, and have the computational infrastructure to compare each night's images to previous nights and flag anything that moves. Historically, you could optimize your telescope for some of these requirements at the expense of others, but getting all of them simultaneously at the level needed to catch a rare interstellar visitor was beyond reach. What changed was the convergence of three technologies in the early 21st century: large-format digital cameras that could cover enormous fields of view, increasingly powerful computing that could process the resulting massive data volumes in near real time, and advanced software algorithms that could automatically search those processed datasets for moving objects. These three threads came together in a new generation of survey telescopes that began coming online in the 2000s and 2010s, and Pan-STARRS was one of the earliest and most capable members of that generation. Pan-STARRS began full science operations in 2010 on the summit of Haleakala. Its primary camera, the orthotelescopic array, contains 1.4 billion pixels arranged in a mosaic that covers a field of view roughly 3 degrees across, about 6 times the diameter of the full moon. In a single 45-second exposure, it can photograph a patch of sky containing more stars than there are people on Earth. Its automated data reduction pipeline processes each night's images and cross-references them against a catalogue of known positions, flagging anything that has moved or changed. The human element, the czar in internal parlance, reviews the most interesting automated detections and decides which ones to submit to the Minor Planet Center for official processing. By the time Oumuamua arrived in the fall of 2017, Pan-STARRS was the most productive asteroid discovery telescope in history. It had found thousands of near-Earth asteroids, hundreds of comets, and catalogued millions of solar system objects. But for interstellar objects, smaller, darker, faster than most solar system bodies, it was barely adequate. Oumuamua was at the absolute edge of Pan-STARRS' sensitivity when Werik spotted it. A slightly smaller object, a slightly less favourable geometry, a slightly different trajectory, and it would have slipped through unnoticed. Which raises an unsettling implication. If Pan-STARRS, operating for 7 years, caught exactly one interstellar object during that time, and if that one object was close to the detection limit, then there must be many interstellar objects passing through our solar system that Pan-STARRS entirely missed. The number density of interstellar objects inferred from the single Oumuamua detection was startlingly high, roughly 0.1 objects per cubic astronomical unit, implying that at any given time there might be tens of thousands of Oumuamua-sized or larger interstellar objects within the orbit of Neptune. Not detectable with Pan-STARRS, not detectable with any then existing instrument, but there, in the dark, drifting through our neighbourhood. We had been living in a solar system embedded in this invisible traffic for billions of years and never known it. Once Werik confirmed the discovery on the morning of October 20th, 2017, the global astronomical community mobilized with a speed and coordination that reflects how extraordinary the situation was. In normal circumstances, telescope time is allocated months or sometimes years in advance. Observatories follow carefully planned schedules. Switching from one target to another requires advance approval, scheduling discussions, and sometimes the disappointment of other researchers whose programs get bumped. None of that applied now. Every major observatory on Earth immediately understood what this discovery meant, and in a collective act of scientific triage, the world's telescopes were redirected. ESO's Very Large Telescope in Chile, a facility consisting of 4 8.2-metre telescopes at Paranal Observatory, was among the first to get observations. Karen Meach, an astronomer at the Institute for Astronomy at the University of Hawaii and a member of the Pan-STARRS discovery team, coordinated an international response that gathered data from observatories spanning the globe. The Gemini North Telescope on Mauna Kea, the William Herschel Telescope in the Canary Islands, the Keck Observatory, the Hubble Space Telescope. Each instrument added another piece of the picture, and the picture that assembled from those pieces was deeply peculiar. The first and most immediately obvious feature was colour. Multiple independent teams analysing independent datasets all reached the same conclusion. Oumuamua was distinctly reddish. Not dramatically red in the way that Mars, for example, is obviously red to the naked eye. The difference was subtle, detectable only through careful spectrophotometric analysis. But it was real and consistent. The object reflected more red light than blue light, producing what astronomers call a red slope in its spectrum. This kind of reddish coloration has a well-understood origin in the outer solar system. Objects that have spent billions of years exposed to the harsh radiation environment of space, bombarded continuously by cosmic rays, energetic particles from the sun, and ultraviolet radiation, develop altered surface chemistry. The radiation drives reactions among organic compounds in the surface material, creating complex carbon-rich molecules called tholins. Tholins are characteristically dark red, and they are found on a wide variety of outer solar system objects. The surfaces of Kuiper belt objects, the irregular dark reddish patches on cometary nuclei, the reddish outer surfaces of some of Jupiter's Trojan asteroids. The presence of tholins indicates an object that has been radiation processed for an extended period. For Oumuamua, the reddish surface colour was consistent with an object that had spent an enormous amount of time in interstellar space, millions or hundreds of millions of years, exposed to the steady bombardment of galactic cosmic rays. The outer layers of whatever material it was made of had been transformed into a dark, processed crust. This was not surprising for an interstellar visitor. It was exactly what you would expect. What happened next in the data analysis was considerably more surprising. As the telescopes tracked Oumuamua over the days following discovery, measuring its brightness at regular intervals, something extraordinary emerged from the light curve. The object's brightness was changing, not in the gradual, smooth way that you might expect from an object slowly rotating on a fixed axis, the kind of variation you see from a slowly tumbling potato-shaped asteroid. No, Oumuamua's brightness was oscillating dramatically, swinging by a factor of roughly 10 over a period of approximately 7 to 8 hours. It would be relatively bright for a while, then dramatically dim, then back to bright, going through this cycle in a way that defied any simple rotational model. For context, an object that varies in brightness by a factor of 10 purely through rotation must have either a very unusual shape or be tumbling in a very unusual way. If you imagine a perfectly spherical object rotating in space, its brightness doesn't change at all. It looks the same from every angle. If you imagine a slightly elongated object like a football, rotating so that you alternately see its broad side and its narrow end, you might see brightness variations of a factor of 2 or perhaps 3. Even the most elongated objects we knew of in the solar system before 2017, lumpy potato-shaped asteroids with axis ratios of maybe 3 to 1, showed brightness variations of at most a factor of 3 to 5. A factor of 10 required an object so extremely elongated or flat that it was genuinely unprecedented in the solar system catalogue. Furthermore, the brightness variations were not perfectly regular. The period kept shifting subtly. The same peak brightness kept recurring, but the timing between peaks was not constant in the way you would expect from a simple, single-axis rotation. This irregularity is the telltale signature of what astronomers call tumbling, or excited rotation. The object was not spinning cleanly around a single axis, but wobbling, rolling, precessing in a complex compound motion around multiple axes simultaneously, like a football thrown by a bad quarterback that spirals and wobbles at the same time. Getting a small solid body into an excited rotational state typically requires some kind of perturbation, a collision, a close gravitational encounter, or internal stresses from outgassing. Once in an excited state, a body tends to stay there unless it can dissipate energy through some internal process. For this to happen and be maintained, the object would need to have significant internal rigidity. It could not be a loose rubble pile, which would quickly damp the tumble by rearranging its internal mass. Oumuamua was tumbling. It was probably solid throughout, and it was shaped in a way that pushed far beyond the boundaries of anything we had catalogued in our own solar system. The Spitzer Space Telescope's attempt to observe Oumuamua in infrared wavelengths added another layer of strangeness. Spitzer was looking for thermal emission, the heat radiated from the object's surface as a result of absorbing solar energy. For an object of Oumuamua's estimated size and distance from the Sun at the time of Spitzer's observation, A straightforward calculation suggests that a certain amount of heat should be detectable, but Spitzer found nothing. The object was invisible in the infrared. The non-detection placed constraints on the object's size and reflectivity. The smaller and more reflective the object, the less heat it would emit, and the harder it would be to detect. Oumuamua had to be either smaller than originally estimated or more reflective, or both. Highly reflective interstellar objects are unusual and difficult to explain. Everything we know about the radiation processing of surfaces in space suggests that surfaces darken over time. A fresh, clean ice surface can be highly reflective, but cosmic radiation transforms ice into tholins, which are dark. The reddish colour of Oumuamua's surface was consistent with tholins. Dark, radiation-processed material, but dark material absorbs more heat and should be more easily detected in the infrared. The combination of a reddish, presumably dark, surface and an infrared non-detection was internally somewhat contradictory, and different researchers resolved the contradiction in different ways. Some suggested that Oumuamua had an unusually fresh or clean outer layer, perhaps the dark tholin crust on the outside, but highly reflective icy material exposed through sublimation or collisional disruption. Others suggested the object was simply smaller than the initial size estimates, and that both its faint brightness and its Spitzer non-detection were consistent with a smaller, somewhat reflective object. Others simply noted the contradiction, and filed it under the growing list of things about Oumuamua that didn't fit any clean model. The most significant observation, the one that would define the scientific debate for years to come, was the absence of any cometary activity. As Oumuamua passed through the inner solar system, multiple telescopes specifically searched for any sign of a coma. The fuzzy, diffuse cloud of gas and dust that surrounds an active comet's nucleus as solar heating drives the sublimation of volatile material from its interior. They found nothing. No coma, no tail, no jets, no spectroscopic signatures of any outgassing molecules, no water vapour, no carbon dioxide, no carbon monoxide, no hydroxyl radicals, nothing. This was deeply significant. Oumuamua passed within 37 million kilometres of the Sun, inside the orbit of Mercury. That is more than close enough to heat any reasonable concentration of volatile ices, water, carbon dioxide, methane, to the point of sublimation. A comet at that distance should be actively venting material in jets that would be clearly visible in spectroscopic observations. Even an object with a protective insulating crust over most of its surface should show some activity. The fact that Oumuamua showed nothing whatsoever led most researchers to initially classify it as an interstellar asteroid, a dry rocky body with no volatile content from another star system. But asteroid turned out to be too simple. Everything about Oumuamua was too simple in the wrong ways. Let's spend considerable time with the shape of Oumuamua, because the shape is where the strangeness becomes most visceral and most difficult to explain. The shape is the thing that most clearly separates Oumuamua from anything we have seen before, and the debate over what shape it actually had, cigar or pancake, turns out to matter a great deal for how we interpret everything else about it. The fundamental problem in determining Oumuamua's shape is that we never directly imaged it. Not even Hubble, the sharpest optical telescope in orbit, could resolve any detail whatsoever. Oumuamua appeared as a point of light in every image taken of it, a dot, a pixel, a blur. Everything we know about its shape is inferred from its light curve, from the way its brightness changed over time as it tumbled through space. This kind of shape determination from brightness variations is called photometric light curve analysis, and it is a well-developed technique in planetary science, used routinely to characterize the shapes of asteroids. But it has limitations, particularly for objects as unusual and as briefly observed as Oumuamua. Here is the basic logic. When an irregularly shaped object tumbles in space, it alternately presents its largest cross-section to an observer and its smallest cross-section. When you see the largest face, the object reflects the most light and appears brightest. When you see the smallest cross-section, the object edge-on essentially, it reflects the least light and appears dimmest. The ratio between the maximum brightness and the minimum brightness in the light curve is related to the ratio of the largest to the smallest cross-sectional area, which in turn constrains the object's shape. A very dramatic brightness variation implies a very extreme shape. Oumuamua's brightness variations, factor of 10 over the observation period, implied something extraordinary. If you assume the object is an elongated shape, like a cigar or a cucumber, and the brightness variation comes from rotating end over end so that sometimes you see the long side and sometimes you see the short end, then the axis ratio needs to be at least 6:1, and probably closer to 10:1, 10 times longer than it is wide. No natural object in our solar system has an axis ratio anywhere close to that. The most elongated asteroids we have catalogued top out at about 3:1. Getting to 10:1 for a solid body formed by natural processes strains credulity. But wait, the cigar model has competition. In 2018, researcher Sergei Mashchenko and others argued that a flat pancake-like shape, an oblate spheroid, wider and longer than it is thick, could produce equally dramatic brightness variations when tumbling. The key insight is that a flat object tumbling chaotically alternates between presenting its flat, wide face to the observer, very bright, and its thin edge, very dim, and the probability distribution of orientations for a tumbling flat object produces brightness variations that can match Oumuamua's light curve as well as or better than the elongated cigar model. Statistically, the pancake is actually somewhat more likely. If you imagine randomly tossing a coin in space and watching it tumble, you would see its face much more often than its edge, meaning that dramatic dimming events would be rarer for a coin than for a cigar, which matches what was observed for Oumuamua. The distinction matters for more than purely aesthetic reasons. A cigar-shaped Oumuamua, if roughly 10 times longer than it is wide, implies very specific size estimates in combination with the brightness data. Roughly 400 to 800 meters long and 40 to 80 meters wide, give or take. A pancake-shaped Oumuamua might be 100 meters by 100 meters in extent but only 15 to 20 meters thick. The mass, surface area and cross-sectional area relative to mass, which turns out to be critical for the non-gravitational acceleration story, are all different between these two models. And both models are genuinely consistent with the available data, which means neither can be definitively ruled out. What both models agree on is that Oumuamua's shape is wildly unusual. Whether it is a cigar or a pancake, its proportions are far outside the range of anything we have catalogued in our solar system. No known natural process reliably produces objects this extreme. Not collisional fragmentation. When two asteroids collide and one shatters, the fragments tend to be irregularly lumpy but not wildly elongated. Not the grinding and erosion of repeated small impacts, which tends to round objects over time. Not tidal disruption by gravity, which can elongate or flatten objects but typically produces shapes that are unusual without being record-breaking. The shape of Oumuamua seems to require either very specific and unusual formation conditions, or a process of sculpting during its long interstellar journey, or something else entirely that we have not yet identified. Some researchers proposed that the shape might have been sculpted by sublimation during Oumuamua's passage through our inner solar system, or, more ambitiously, over millions of years of exposure to the interstellar radiation field. The principle is similar to what happens to a bar of soap as you use it. Material is removed from surfaces gradually, and the remaining shape can evolve towards something more elongated as you go. If Oumuamua originally had some volatile rich regions and some volatile poor regions, differential sublimation over its long journey might have carved away some areas more than others, creating an increasingly extreme shape. But the details of how this would produce an object 10 times longer than it is wide, without completely destroying it, are unclear. Others turn to the idea of tidal disruption from a close encounter with a massive body, a star or even a stellar mass black hole. Objects passing close enough to a neutron star or black hole experience enormous differential gravitational forces that can stretch and sculpt them dramatically. A planetesimal that passed within the tidal radius of a compact object early in its history might have been elongated or flattened, then flung outward into interstellar space carrying that extreme shape with it. The math works in principle, but the probability of any given interstellar object having such a dramatic history seems low, though with many trillions of interstellar objects in the galaxy, low probability events still happen. The shape remains unexplained in any fully satisfying way, and the shape is also ultimately only the second strangest thing about Oumuamua. Of all the mysteries surrounding Oumuamua, the non-gravitational acceleration is the most technically challenging, the most rigorously documented, and the most difficult to explain without invoking something unusual. This is where the story went from surprising but probably natural to genuinely baffling. And it is the data point that spawned the most exotic scientific hypotheses, including the alien one. In June 2018, 8 months after the discovery, a team of astronomers led by Marco Micheli at ESA's Near-Earth Object Coordination Center published a paper in the journal Nature. The paper was the product of careful, painstaking astrometric analysis, the precise measurement of an object's position in the sky at multiple points in time, which allows the reconstruction of its trajectory. Micheli's team had gathered every available positional measurement of Oumuamua from every telescope that had observed it, from the original Pan-STARRS detection through the last moments it was bright enough to track. They then fitted the most accurate gravitational model they could construct, taking into account the gravitational influence of every planet, even the tiny perturbations from the more distant outer planets, to that dataset. And when they compared the model to the actual observations, there was a residual, a systematic offset that grew over time. Oumuamua was not where pure gravitational dynamics predicted it should be. It was slightly farther from the Sun than gravity alone could explain. Something was pushing it outward, an additional force acting on top of gravity, and that force had the specific signature of being proportional to the inverse square of the distance from the Sun. In other words, it was twice as strong at half the distance, 4 times as strong at a quarter the distance. The way solar energy, whether in the form of radiation or as the driver of sublimation processes, scales with distance. The team was rigorous about ruling out mundane explanations. Could it be a measurement error? They checked and rechecked. The residuals were too large and too consistent to be artifacts. Could it be a systematic bias in the ephemeris model? They evaluated every possible source of systematic error. Could it be the Yarkovsky effect, a subtle force that acts on rotating objects due to the asymmetric heating and cooling of their surfaces by sunlight? Which applies to solar system asteroids? Yes, but the Yarkovsky effect for an object of Oumuamua's estimated size would be far too small to produce the observed acceleration. The non-gravitational acceleration was real, it was substantial, and it was behaving exactly like the force that outgassing produces on comets. The force from outgassing on comets works like a rocket engine. As solar heat sublimates ice from a comet's nucleus, the resulting gas jets spray outward into space. By Newton's third law, the gas jet pushing outward pushes the comet in the opposite direction. This is a small force, a rocket thruster made of evaporating ice, not burning propellant, but for small objects, the cumulative effect over days and weeks of activity adds up to measurable trajectory deviations. Astronomers routinely account for this non-gravitational force when computing comet trajectories, and the standard parameters for describing it are well calibrated against decades of comet observations. Here is the problem with applying this explanation to Oumuamua. The magnitude of the observed non-gravitational acceleration was quite large compared to what you would expect from the object's estimated size and the visible outgassing that was not there. When you calculate how much gas would need to be ejected to produce the observed push, you get a number that is substantially more than you would expect from an object showing no visible coma. Not just a little more, significantly more. For standard cometary volatiles like water, carbon dioxide, or carbon monoxide, the amount of outgassing required to produce Oumuamua's acceleration would generate a coma detectable by the instruments that were specifically searching for one, unless the outgassing was in a form that those instruments couldn't detect. And this is where the story begins to branch into competing hypotheses. The physics of what could be accelerating Oumuamua without producing a visible coma falls into 2 broad categories. First, outgassing of an unusual volatile that is invisible to the instruments used. Second, some non-outgassing mechanism such as radiation pressure on an extremely thin and light structure. The first category is where most serious natural explanations live. The second category, at its logical extreme, lands you at Avi Loeb's light sail. Let's understand the radiation pressure argument properly before we discuss it in the alien context. Solar radiation pressure is a real, well-understood physical force. Photons from the sun carry momentum, and when they strike a surface, they transfer a tiny amount of that momentum to the surface. For ordinary-sized objects, anything from a planet down to a typical asteroid, this force is negligibly small compared to gravity. But for an object with an extremely high ratio of surface area to mass, something very large in area but very small in mass, radiation pressure can become significant. This is the principle behind solar sails. By making a spacecraft very thin and covering it with a large reflective surface, you can achieve propulsion from nothing but sunlight. For radiation pressure to explain Oumuamua's observed acceleration, the calculation produces a specific required ratio of area to mass. The object would need to have a surface area to mass ratio roughly 20 times greater than any known solar system asteroid or comet. For a solid object with any reasonable material density, achieving this ratio implies extreme flatness. The object would need to be something like 0.3 to 0.9 millimeters thick while being tens of meters across. That is thinner than the thinnest aluminum foil extended to the area of a basketball court. No known natural process produces structures like this. The proposition that an interstellar rock could be a fraction of a millimeter thick while spanning tens of meters is so far outside the range of anything in our solar system catalogue that it effectively rules out radiation pressure as the explanation for a natural object, which leaves either an unusual but natural outgassing mechanism we had not previously considered or an artificial structure. Here we need to spend real time on Avi Loeb, his argument, and the debate it sparked, because dismissing it too quickly would be intellectually dishonest. The hypothesis deserves a serious treatment, which means understanding both its logic and its problems. Avi Loeb is not a crank. He spent years as the chair of Harvard University's astronomy department, one of the most prestigious academic positions in the field. He is the founding director of the Harvard-Smithsonian Center for Astrophysics Institute for Theory and Computation. He has published hundreds of peer-reviewed scientific papers on topics ranging from the epoch of reionization in the early universe to the physics of black holes to the search for extraterrestrial life. He is genuinely respected as a scientist in many of these areas, even by colleagues who find his Oumuamua conclusions overreaching. He's also deeply involved in the Breakthrough Starshot initiative, funded by Russian-Israeli billionaire Yuri Milner. Breakthrough Starshot is a serious scientific and engineering project, not a fringe venture, that aims to develop gram-scale light-sail spacecraft that can be accelerated by a powerful ground-based laser array to a significant fraction of the speed of light, enabling them to reach the Alpha Centauri system within decades rather than millennia. The physics of light-sail propulsion is well understood. The engineering challenges are enormous, but not in principle insurmountable. Light sails are real technology. The Japanese spacecraft Icaros successfully demonstrated solar sail propulsion near Venus in 2010, and the Planetary Society's Light Sail 2 mission demonstrated solar sailing in Earth orbit. The concept is not science fiction, so when Loeb looked at the numbers for Oumuamua's non-gravitational acceleration and ran the calculation for radiation pressure, the result produced a required area-to-mass ratio that is physically impossible for a natural solid object, but is physically plausible for a purpose-built light sail. That is the kernel of his argument. Not that aliens built it for certain, not that it was flying toward Earth on a mission, just that the numbers are consistent with a light sail and inconsistent with a natural solid object, and therefore a light sail of artificial origin should be taken seriously as a hypothesis. In November 2018, Loeb and his colleague Shmuel Bialy published a paper in the astrophysical journal Letters titled "Could Solar Radiation Pressure Explain Oumuamua's Peculiar Acceleration?" The paper was formal, measured, and careful in its language. The authors noted that the radiation pressure explanation for the non-gravitational acceleration required an area-to-mass ratio that natural objects cannot achieve. They then explored what kind of structure could have such a ratio, and they concluded that a light sail, a thin, wide, reflective surface, would fit the observational constraints. They offered 2 specific scenarios. Either Oumuamua was debris from a defunct artificial light sail, tumbling through the galaxy after its mission ended, or it was a fully functional probe intentionally sent toward our solar system. The paper landed like a meteor. Within days it had generated thousands of media stories worldwide. Within weeks it had been downloaded from the Astrophysical Journal server more times than almost any paper in the journal's history. It put the question of alien technology at the center of a mainstream scientific debate in a way that had not happened before, and it prompted an immediate, vigorous, and in some cases quite harsh response from the broader astronomical community. The criticisms came from multiple directions, and they were substantive. First, The light sail hypothesis requires an object of extraordinary thinness that would almost certainly be destroyed by the bombardment of interstellar dust and gas during its journey between star systems. A structure a fraction of a millimetre thick, extended over an area of hundreds of square metres, would be shredded by the continuous impact of interstellar particles. Any civilization capable of building such a sail would need to know this. Second, a light sail tumbling freely, as Oumuamua was tumbling, would not receive radiation pressure in a simple, constant direction. The force would oscillate dramatically as the sail presented different faces to the Sun, producing an erratic rather than smooth acceleration. But Oumuamua's non-gravitational acceleration was smooth and consistent with a constant direction, which is more consistent without gassing than with a tumbling sail. Third, simulations showed that a tumbling flat surface pushed by radiation pressure would not only be accelerated away from the Sun, but also pushed significantly sideways, perpendicular to the Sun-Oumuamua direction, but Oumuamua's trajectory showed no such lateral component. Fourth, if Oumuamua were a thin, flat structure with a high surface area to mass ratio, it should occasionally have been seen nearly edge-on during its tumbling, at which point it would have been far too dim to detect, but it was tracked continuously without any such dimming events. Loeb addressed some of these criticisms and disputed others. He argued that the statistics of the tumbling would not necessarily produce the expected dimming events within the observation window. He noted that some of the objections were based on assumptions about the object's structure and composition that were themselves uncertain. He maintained that the key fact, the non-gravitational acceleration implying an area-to-mass ratio inconsistent with a natural solid object, had not been adequately addressed by any natural hypothesis. What is genuinely valuable about the alien hypothesis debate, regardless of its ultimate resolution, is what it forced. It forced astronomers to work harder on natural explanations than they might otherwise have done. It forced a public discussion about the scientific culture around extraterrestrial intelligence that was long overdue, and it crystallized for a wide audience just how genuinely strange Oumuamua was. Not strange if you look at it from this particular angle, strange. Genuinely, documentably, measurement-based, strange. Loeb followed the Astrophysical Journal paper with a best-selling popular book in 2021, Extraterrestrial, the First Sign of Intelligent Life Beyond Earth, which brought the debate to a far wider audience. He then founded the Galileo Project at Harvard, dedicated to systematically searching for evidence of extraterrestrial technology using scientific instrumentation, including all-sky monitoring networks designed to detect anomalous aerial phenomena. He has become, for better or worse, the most prominent public face of the argument that SETI, the search for extraterrestrial intelligence, should be treated as a serious observational science rather than a fringe pursuit. The majority of the planetary science community remains skeptical of his Oumuamua conclusions, while acknowledging that the underlying question, are there natural explanations that fully account for everything we observed, has not been completely settled. And in 2023, the strongest natural explanation yet emerged to challenge the alien hypothesis directly. While Avi Loeb was writing books and founding institutes, a substantial community of astronomers was doing something quieter, but arguably more scientifically productive, working systematically through every natural explanation they could think of and checking each one against the available data. This is how science is supposed to work. You do not accept the most exotic explanation just because it fits the data. You first make sure you have genuinely exhausted the less exotic alternatives. The first major natural hypothesis to gain traction was the nitrogen ice model, proposed by Stephen Desch and Alan Jackson at Arizona State University in 2021. Their idea was this: Oumuamua could be a fragment from the outer mantle of a Pluto-like body, a nitrogen-rich dwarf planet from another solar system. The outer layers of Pluto and similar bodies are rich in nitrogen ice, which can sublimate at temperatures relevant to the inner solar system. If a large impact in some distant planetary system shattered a Pluto equivalent and sent fragments flying outward, those fragments would carry nitrogen ice with them. As such a fragment approached our Sun, the nitrogen ice would sublimate, producing nitrogen gas, a molecule with no strong spectroscopic signatures in the wavelengths typically used to search for cometary activity, and essentially invisible against the background. The resulting gas thrust could provide exactly the observed non-gravitational acceleration with no detectable coma. The nitrogen model had elegant explanatory power. Nitrogen sublimation produces a force of the right magnitude, Nitrogen gas is nearly invisible to most standard detection methods. The process of mass loss from sublimation, happening differentially across the object's surface as it tumbled, could naturally sculpt a more elongated or flattened shape over time, and the specific colour and reflectivity of nitrogen ice-rich objects is consistent with some of Oumuamua's observed properties. The problem was the statistical improbability. How many Pluto-like bodies would need to have been disrupted in the galaxy to produce even one nitrogen ice shard of Oumuamua's size passing through our solar system within the observing window of Pan-stars? The answer was enormous, far more than current stellar evolution models can accommodate. The mass of nitrogen ice in the interstellar medium implied by this hypothesis would exceed the total nitrogen budget of planetary systems by a large margin. The model explained Oumuamua, but at the cost of requiring a universe with far more Pluto disruption than we have any other evidence for. The molecular hydrogen ice model, proposed by Daryl Seligman and Gregory Laughlin in 2020, faced different but equally serious problems. Molecular hydrogen, H2, can exist as a solid only at temperatures very close to absolute zero, around minus 259 degrees Celsius. In that phase, H2 ice has unusual optical properties. When it sublimates, it produces no dust and is essentially transparent and invisible to most telescopes. An H2 iceberg warming in sunlight would produce a steady thrust of invisible gas, providing exactly the observed non-gravitational acceleration without generating any detectable coma, and the process of sublimation would naturally sculpt the object into progressively more elongated or flattened shapes. But molecular hydrogen ice is extraordinarily difficult to form and extraordinarily fragile once formed. It only condenses in the coldest cores of dense molecular clouds, vast interstellar gas structures where temperatures approach absolute zero, and then it can only survive the journey from such a cloud to our solar system if the journey is short enough and cold enough that starlight doesn't evaporate it. Calculations showed that a hydrogen iceberg large enough to be Oumuamua would need to have formed within the last few tens of millions of years and within a few kiloparsecs of our solar system, conditions that are not impossible but are quite restrictive, and there were concerns about whether such icebergs could form at all in realistic molecular cloud conditions when you account for the small grain sizes involved. Seligman acknowledged these problems. He is a researcher who follows the evidence. When a hypothesis is shown to have a fatal flaw, he revises it. Which leads us to the 2023 proposal that emerged from his collaboration with Jennifer Bergner. Bergner is an astrochemist at the University of California, Berkeley, whose research focuses on the chemical reactions that occur on the surfaces of icy bodies in space. Her laboratory experiments involve irradiating ice mixtures with high-energy particles to simulate the effects of cosmic rays and measuring what chemical species are produced. In December 2022, a colleague described Oumuamua's properties in a seminar, and something Bergner knew from her lab work clicked into relevance. When water ice is bombarded with cosmic rays, which is something that happens continuously to any ice-bearing object in interstellar space, the radiation can split water molecules into their constituent atoms and ions. Some of the resulting hydrogen doesn't immediately escape. Instead, it gets trapped in the ice matrix as molecular hydrogen gas, H2, stored in tiny pockets and channels within the solid structure. Over millions of years of continuous irradiation, a comet-sized water ice body accumulates an enormous reservoir of trapped H2. When such an object then warms up, by passing close to a star for instance, the trapped gas expands, fractures the surrounding ice matrix and escapes. This process produces a sustained outgassing force from molecular hydrogen, driving the kind of non-gravitational acceleration observed for Oumuamua. And because the hydrogen coma is in ultraviolet wavelengths that Earth's atmosphere absorbs, it would be completely invisible to ground-based telescopes. Crucially, this hypothesis does not require exotic materials or improbable conditions. Water ice is the most common solid volatile in the universe. Cosmic ray irradiation of water ice in interstellar space is a normal, well-documented process. The trapping of H2 within irradiated water ice has been demonstrated in laboratory experiments. Bergner and Seligman calculated that the amount of trapped H2 expected in a water ice body after millions of years of cosmic ray bombardment could plausibly account for the observed acceleration of Oumuamua given its estimated size. They published their results in Nature in March 2023. The reaction from the community was more positive than previous natural hypotheses had received, partly because the mechanism was simpler, more physically grounded, and more chemically plausible than either nitrogen ice or pure hydrogen icebergs. But it was not universally embraced. Loeb argued that the surface temperature calculations were incorrect, and that the outgassing would have to occur primarily from the interior rather than the surface, creating a different geometry for the force. Others pointed out that the model required Oumuamua to be almost entirely made of water ice, but the spectral colour data suggested a radiation-processed, tholin-covered surface inconsistent with freshwater ice. Still others noted that if this mechanism was so common, we should expect many more comets to show similar non-gravitational accelerations without visible comas. But this last objection had already been partially addressed. Seligman, Bergner and colleagues, working with the Oumuamua question in the background, had identified a collection of solar system objects they called dark comets, bodies that show small non-gravitational accelerations without any visible cometary activity. By 2024, the catalogue of confirmed dark comets had grown to around 14 objects, suggesting that whatever process drives Oumuamua's behaviour is not entirely unique. Whether the dark comet phenomenon is directly analogous to Oumuamua's situation is unclear. Oumuamua's acceleration was much larger than those of the identified dark comets, and the mechanism may be the same or may be different. But the existence of dark comets suggests that the spectrum of cometary behaviour is considerably broader than astronomers had appreciated before 2017. The scientific debate over what Oumuamua was remains genuinely open as of today. Most planetary scientists consider the hydrogen from irradiated water model, or some variant of it, to be the most plausible natural explanation currently available. It has no obvious fatal flaw, it is consistent with known chemistry and known physics. It makes predictions that can be tested against future interstellar objects. But it has not been proven, and Loeb and others continue to argue that the natural explanations fall short in specific ways that keep the artificial origin hypothesis alive. Science sometimes does not resolve cleanly. Oumuamua is one of those cases. 2 years after Oumuamua shocked the world, the universe offered a second data point, and it could barely have been more different from the first. Gennady Borisov is an engineer who works at the Sternberg Astronomical Institute in Crimea, and who has spent much of his personal time and resources building telescopes from scratch and using them to hunt for comets. By 2019, he had discovered 7 comets and several near-Earth objects with telescopes of his own design and construction. His latest instrument, a 65cm reflector, was nearly complete when he began regular observing with it in the summer of 2019. On the morning of August 30th, 2019, Borisov was conducting a comet search in the pre-dawn sky, a region of sky relatively close to the Sun from Earth's perspective, which most professional survey telescopes deliberately avoid because the bright twilight makes observation difficult. The Atlas and Pan-STAR surveys, for example, don't observe within about 45 degrees of the Sun, because the sky background brightness degrades their sensitivity. Borisov's smaller, simpler telescope was less sensitive to sky background, and more flexible in where it could point, which meant he was looking in a region that larger surveys systematically missed. And in that region, he found something moving in the wrong direction. Objects in our solar system, viewed from Earth, tend to move in predictable directions relative to the Sun. An object at a given distance from the Sun, on a bound orbit, moves in a way that is consistent with the constraints of solar gravity. What Borisov spotted was moving inconsistently with any bound solar orbit. Within days, as the data was distributed and confirmatory observations poured in from around the world, the conclusion was clear. This was a second interstellar object. It received the designation 2A/Borisov. 2 Interstellar Borisov, and amateur astronomer Gennady Borisov had, with a homemade telescope, made one of the most significant discoveries in the history of astronomy. The contrast with Oumuamua was immediate and striking. Where Oumuamua showed no cometary activity whatsoever, Borisov was obviously, exuberantly, unambiguously a comet. From the very first observations, it displayed a bright coma, a fuzzy halo of gas and dust surrounding the nucleus. And as it approached the Sun, the coma brightened and a tail developed, pointing away from the Sun in the classic fashion of solar system comets. Spectroscopic analysis found water vapour. It found carbon monoxide. It found other molecular species. the standard vocabulary of cometary chemistry, present in roughly the abundances that theory predicted. Hubble Space Telescope observations showed a compact star-like nucleus surrounded by a diffuse cloud of material. Whereas Oumuamua appeared to be a rock, Borisov is really active, more like a normal comet, said David Jewett of UCLA, who led one of the Hubble observing teams. It's a puzzle why these two are so different. That puzzle cuts right to the heart of what we were learning about interstellar objects as a class. There apparently is no typical interstellar object. Our first two confirmed visitors were as different from each other as a dry rock and an icy snowball, despite both having been ejected from some other planetary system and travelled through interstellar space to reach us. Borisov was discovered 3 months before its closest approach to the Sun, perihelion, on December 8, 2019, at a distance of approximately 2 astronomical units, giving astronomers far more time to study it than they had had with Oumuamua. The scientific haul was correspondingly much richer. Chemical inventories were compiled, colour maps were made, the coma's evolution over time was tracked as the comet brightened on its inbound journey and then faded on its way out. One particularly striking finding was the high abundance of carbon monoxide relative to water, much higher than is typical for solar system comets observed at comparable distances from the Sun. This could reflect formation conditions in Borisov's home system that were different from those that formed our own Oort cloud comets. In March 2020, Hubble detected what appeared to be a fragment breaking off from Borisov's nucleus. The comet was beginning to disintegrate under the stresses of solar heating, a process common in long-period comets making their first close approach to a star. It was a reminder that Borisov, for all its familiarity, had just made its first ever close approach to any star. It had been drifting in the cold dark of interstellar space for an unknown but very long period, and the sudden warmth was causing structural changes. The disruption was partial. The comet survived intact enough to continue on its trajectory, and by late 2021 it had receded beyond the detection limit of any current telescope. The fact that Borisov looked so familiar, so much like a normal comet, was actually surprising to many researchers, for reasons that cut deep into planetary formation theory. The comets in our own solar system's Oort cloud are thought to be predominantly icy bodies formed beyond the snowline, the distance from the Sun at which water molecules freeze into ice. These icy bodies were then scattered to very large distances by gravitational interactions with the giant planets. Theory predicts that interstellar comets, the ejector of other planetary systems, should have a similar composition because the same physics applies. You expect to mostly eject things from the outer, icy regions of a planetary disk. So Borisov being an icy, active comet was what theory predicted. Oumuamua being apparently dry and rocky was the surprise. This created an interesting tension. Either Oumuamua was a rare exception, one of the smaller fraction of interstellar objects that happen to be rocky, or there is something we fundamentally don't understand about the interstellar object population. Given our sample size of 2, we genuinely cannot tell. It's like flipping a coin twice, getting 1 heads and 1 tails, and trying to determine whether the coin is fair. You can't. You need more data. In the summer of 2025, the universe provided a third data point, and this time we were considerably better prepared. The ATLAS network, the Asteroid Terrestrial Impact Last Alert System, is a NASA-funded global survey network designed primarily for last alert planetary defense, catching asteroids on short notice before they could impact Earth. Its telescopes, located in Hawaii, South Africa, Chile, and the Canary Islands, cover the visible sky multiple times per night. On July 1, 2025, the ATLAS telescope at the Rio Hurtado Observatory in Chile detected a new object in images taken earlier that morning. The object was provisionally designated A11PL3Z, then C/2025 and 1, and within days of the initial report it was clear this was something extraordinary, a third interstellar object. It was officially designated 3I/Atlas. 3I/Atlas arrived in our solar system with more energy than either of its predecessors. Its orbital eccentricity was approximately 6.14, far beyond Borisov's 3.36 and vastly beyond Oumuamua's 1.188. Its hyperbolic excess velocity, the speed at which it was moving when still far from the Sun's gravitational influence, was approximately 60 kilometers per second. To put that in context, Oumuamua's hyperbolic excess velocity was about 26 kilometers per second, and Borisov's was about 32 kilometers per second. 3I/Atlas was arriving faster than both, carrying more kinetic energy per unit mass, suggesting it came from a region of the galaxy where relative velocities between stars and drifting objects are higher, possibly from the inner galaxy, or from a source that was itself moving rapidly. 3I/Atlas showed cometary activity essentially from its discovery, displaying a coma and a developing tail. In that sense, it was more Borisov-like than Oumuamua-like. It reached perihelion on October 29, 2025, passing at a distance of about 1.357 astronomical units from the Sun, farther than either of its predecessors in their closest approaches. At closest approach to Earth, it was still about 270 million kilometers away, well beyond any threat. The response from the astronomical community to 3I/Atlas was notably more organized and more productive than the scramble that followed Oumuamua's discovery, reflecting the lessons learned and the infrastructure built in the intervening 8 years. Multiple major observatories had response protocols ready. The James Webb Space Telescope was turned toward it. ALMA, the Atacama Large Millimeter/Submillimeter Array in Chile, analyzed its gas composition with unprecedented sensitivity. The Vera C. Rubin Observatory, which had just begun scientific operations months earlier, contributed observations. The result was a much richer chemical characterization than had been possible for either Oumuamua or Borisov. The chemical profile emerging from early analyses of 3I/Atlas was genuinely striking. High abundances of methanol, elevated carbon monoxide, isotopic ratios, the specific proportions of different forms of the same chemical elements, that appeared in preliminary studies to be very different from what is typical of solar system comets. One analysis, released as a preprint in early 2026, suggested that the isotopic signature was consistent with the comet having formed in an extremely old and extremely cold environment, potentially one of the very first generation of star-forming regions in the early universe, implying an age for the object that could rival or exceed 10 billion years. If confirmed, this would make 3I/Atlas a literal relic of the early cosmos, a piece of chemistry from a time when the universe was less than 4 billion years old, preserved in cold storage for most of cosmic history before wandering through our solar system. This interpretation is preliminary and requires extensive confirmation, but it illustrates what interstellar objects represent as scientific resources. Our telescopes cannot directly analyze the chemistry of early universe environments at the detail level possible here, but an interstellar comet formed in those environments can carry that chemistry with it, intact, frozen in ice for billions of years, and deliver it to our telescopes for analysis. It is a kind of cosmic time capsule service that we had not previously been able to access. 3 interstellar objects in 8 years, after billions of years of astronomy producing 0. The obvious interpretation is not that the universe suddenly started sending more visitors, it is that we finally built the eyes to see them. And as the Vera C. Rubin Observatory moves into its full survey operations over the next decade, the rate of discoveries is expected to accelerate dramatically. One of the most haunting aspects of the Oumuamua story is the acute awareness of how much we didn't learn, and couldn't learn, simply because we weren't ready. The discovery was not just scientifically important, it was a stress test of humanity's preparedness for exactly this kind of event, and the stress test revealed significant gaps. The most obvious gap was spacecraft. At the moment of Oumuamua's discovery, there was no spacecraft on Earth capable of catching it. Catching an object moving at 26 kilometers per second relative to the Sun, already past its closest approach and accelerating outward, would require a mission launched with extraordinary urgency and carrying propulsion systems that could achieve velocity changes far beyond what was available. Multiple mission concept studies were performed in the weeks and months after the discovery, and they all reached the same conclusion. It was possible, in principle, to send a spacecraft to intercept Oumuamua using available launch vehicles. But the transit time would be measured in decades, by which point the scientific value of the rendezvous would be severely degraded, given that Oumuamua would be billions of kilometers from the Sun in extreme cold. The Project Lyra study, conducted by the Initiative for Interstellar Studies and published in late 2017, examined the feasibility of a mission to Oumuamua using a variety of propulsion strategies, including Jupiter gravity assists, solar obverse maneuvers, and hypothetical solar sail technologies. Their conclusions: it was not impossible, but it was very difficult and would require mission concepts pushing at or beyond the current state of the art. A spacecraft launched within a few years of discovery using a Jupiter flyby for additional speed boost might reach Oumuamua in the 2050s, when the object would be roughly 250 astronomical units from the Sun. That is a feasible mission architecturally, but the science return from a rendezvous at such extreme distance and cold would be uncertain. In response to this gap, the European Space Agency moved forward with the Comet Interceptor mission. The concept is elegant in its strategic logic. Rather than designing a mission to a specific already known target, Comet Interceptor is designed to be launched before a target is identified, placed at a gravitationally stable waiting point in space, the Sun-Earth Lagrange point 2, roughly 1.5 million kilometers from Earth in the direction away from the Sun, and kept in readiness. When an appropriate target is identified, a long-period comet on its first inbound journey, or an interstellar object, the spacecraft can be dispatched from its waiting location. This is the planetary science equivalent of keeping a fire truck idling in the station rather than trying to build one after the fire starts. Comet Interceptor consists of a primary spacecraft and two smaller probes designed to approach a cometary or interstellar target from multiple directions simultaneously. It is currently planned for launch in 2029 aboard an Ariane 6 rocket. The Vera C. Rubin Observatory is the other transformative development. Its technical specifications represent a genuine generational leap in survey capability. The 8.4-meter Simony Survey Telescope sits on Cerro Pachon in the Chilean Andes, equipped with the world's largest scientific camera, a mosaic of 189 charge-coupled devices, CCDs, totaling 3.2 gigapixels, covering a field of view of 9.6 square degrees, roughly 40 times the apparent area of the full moon, in a single 15-second exposure. The telescope can complete a full survey of the visible sky in roughly 3 nights, and it does this continuously, building a time-lapse record of the entire southern sky that automatically reveals anything that moves. Its computational infrastructure processes data in real time and issues automated alerts within 60 seconds of detecting a transient event. For interstellar objects, Rubin represents a detection capability that is estimated to be orders of magnitude beyond what Pan-STARRS achieved. Where Pan-STARRS might catch one interstellar object over 7 years of operations, Rubin is expected to catch between 5 and 50 over its planned 10-year survey, with some more optimistic models suggesting rates as high as dozens per year if the true number density of interstellar objects is at the upper end of current estimates. The key advantage is depth. Rubin can detect objects significantly fainter than Pan-STARRS could, which means it catches more objects per unit of sky area, and it can detect objects earlier in their trajectory, when they are farther from the Sun and moving more slowly relative to Earth, giving astronomers more time to react. In its first 10 hours of science commissioning operations in 2025, Rubin discovered 2,104 previously unknown asteroids. It found them faster in a single night than most observatories find in an entire year. When fully operational and running its full survey cadence, it is expected to more than triple the total number of catalogued solar system objects within 2 years. For interstellar objects specifically, even the conservative estimate of 5 per decade would transform interstellar object science from a study of individual anomalies into a genuine population study, enabling the statistical analyses that can answer the deeper questions about what these objects represent. Proposals for faster intercept missions are also advancing. Several groups have studied mission architectures using nuclear thermal propulsion, solar obverse maneuvers, where a spacecraft dips very close to the Sun during maximum acceleration to take maximum advantage of gravity and radiation pressure, and even conceptual directed energy acceleration that could push a light probe to a substantial fraction of the speed needed to catch a fast-moving interstellar visitor. The challenge is lead time. You need to identify an interstellar object early enough, when it is still in the outer solar system, to have time to launch and catch it. Rubin's extended detection range may provide exactly that lead time, catching future Oumuamuas months earlier than Pan-STARRS could have, potentially enabling a rapid response spacecraft to be launched and intercept the object before it recedes beyond reach. Let us zoom out now. Let us pull back from the individual objects the specific debates, the technical arguments about hydrogen outgassing and light sails, and think about what the existence of interstellar objects tells us about the cosmos we inhabit. The solar system does not exist in isolation. It never has. We think of it as an island in space, the sun and its planets, orbiting in a void, separated from the nearest star by 4 light-years of nearly nothing. But this picture, while true at one level, misses something important about the deep time physics of how matter moves through the galaxy. Stars pass within a few light-years of each other over geological timescales. Gravitational perturbations from passing stars continuously nudge the outer Oort cloud, kicking comets inward where we eventually see them. And matter ejected from one planetary system during its formation drifts outward indefinitely, eventually populating the interstellar medium with a diffuse but measurable flux of planetary debris. Our solar system has been embedded in this exchange for its entire 4.6 billion year history. Every few million years, on average, a comet or asteroid from another star system drifts through the inner solar system. Before 2017, we had no way to see these visitors. After Pan-STARRS, we saw one. After Rubin, we will see dozens. The picture that is emerging is of a galaxy that is not a collection of isolated stellar systems, but something more like a vast ecosystem, connected by the slow drift of debris, exchanging material across light-year distances over million-year timescales. This exchange has potential implications that are genuinely profound. The most widely discussed is panspermia, the idea that life, or the chemical precursors to life, could be transported between star systems. We know that some microorganisms can survive extreme environments, the vacuum of space, intense radiation, deep freeze, for extended periods. We know that rocks from Mars have reached Earth via meteorite impacts and vice versa. Material is exchanged even between planets within our own solar system. The question of whether material could survive the far harsher conditions of interstellar transit is genuinely uncertain, but it is a scientific question, not just a speculative one. If interstellar objects are common, if there are thousands of them drifting through the inner solar system at any given time, then statistically significant amounts of interstellar material are arriving on Earth on geological timescales. What that material might carry is an open question that the study of interstellar objects can help address. There is also the question of what the interstellar object population tells us about planetary system formation across the galaxy. Every interstellar object is in some sense a sample of its home system. Its composition reflects the chemistry of the protoplanetary disk where it formed. Its size distribution reflects the physics of how planetesimals coalesce and fragment in that disk. Its velocity reflects the dynamical processes that ejected it. A fast object may have been scattered by a gas giant in a chaotic young system, while a slow object may have been gently nudged outward by a close stellar encounter. Reading these properties statistically, across a large sample, will allow astronomers to do something extraordinary, perform comparative planetology at galactic scale, characterizing the range of planetary formation conditions across hundreds or thousands of different stellar environments without ever leaving our own solar system. Borisov, with its relatively familiar cometary chemistry, suggested that at least some other planetary systems form icy bodies in their outer regions in ways broadly similar to our own solar system. 3I/Atlas, with its apparently ancient and exotic chemistry, suggested that the range of formation environments represented in the interstellar population may be very wide, stretching back to the very early universe. Oumuamua, with its apparently dry rocky nature, suggested that rocky ejecta exists in significant quantities in the interstellar population, even though theory predicted it should be rare. Each data point adds a piece to the picture. As Rubin builds the catalogue, the picture will fill in with unprecedented resolution. The question of where Oumuamua specifically came from remains unresolved. Its approach direction, traced backward through the galaxy, pointed toward the general region of the constellation Lyra, not far from the bright star Vega. But not far on the celestial sphere doesn't mean it actually came from Vega. The object was moving slowly enough relative to the local standard of rest, the average motion of nearby stars, that it had probably been drifting for hundreds of millions of years, during which time Vega's position had changed substantially relative to its starting trajectory. No specific home system has been identified for Oumuamua. It may never be. The same is true of Borisov and 3I/Atlas. We can estimate the direction they came from, and researchers have proposed candidate home stars for Borisov, the red dwarf binary Kruger 60, about 13 light-years away, is a plausible candidate given the geometry, but none of these associations are definitive. The interstellar objects we detect are anonymous wanderers. They carry the chemical signature of their origins in their isotopic ratios and molecular inventory, but not a return address. There is one more dimension of the Oumuamua story worth exploring before we conclude, one that goes beyond the pure astronomy and into the deeper questions of how science engages with ideas at its edges. The alien hypothesis debate was not just a scientific argument, it was also an argument about scientific culture, about the norms and taboos that shape what gets investigated and how. Avi Loeb has been most explicit about this. His argument, stripped to its essence, is that the scientific community has an irrational aversion to taking seriously the hypothesis that we might have encountered extraterrestrial technology, and that this aversion is not epistemologically justified. We don't have enough data to rule it out, he says, and the taboo against even seriously considering it means that if such an encounter were to happen, we might fail to recognize it. His critics argue that the alien hypothesis for Oumuamua is not taboo. It has been discussed openly in peer-reviewed journals, debated at scientific conferences, covered extensively in the scientific press. What it lacks is evidence, and this is where the philosophical rubber meets the scientific road. Science does not require extraordinary certainty before investigating a hypothesis. It does require that a hypothesis make testable predictions and that there be some positive evidence in its favour beyond the mere absence of a competing explanation. The case for Oumuamua as an alien artefact rests primarily on what it is not. It is not behaving quite like any natural object we know, rather than on what it is. Negative evidence is evidence, but it is weak evidence. The history of astronomy is full of cases where an anomalous observation that seemed to require an exotic explanation turned out, with better data or better theory, to have a mundane natural explanation. But, and this is important, it is also full of cases where the anomaly was real, and the exotic explanation was correct. The cosmic microwave background looked like an anomaly before it was understood as the afterglow of the Big Bang. Dark matter looked like an inexplicable anomaly in galaxy rotation curves before it was established as a component of the universe. Pulsars, when first discovered, were so regular and so unexpected that half seriously jokingly named LGM-1 for Little Green Men 1 before they were understood as rotating neutron stars. Anomalies are where science grows. The correct response to Oumuamua, the epistemically honest response, is to acknowledge that we don't know what it was. We have competing hypotheses, the most plausible of which is a natural object with unusual properties, the most exotic of which is artificial. We don't have the data to definitively distinguish between them, and our best strategy is to improve our instruments, develop better theories, find more objects, and keep investigating. This is exactly what the astronomical community is doing. The alien debate, while sometimes generating more heat than light in public discourse, has ultimately been productive in pushing the science forward. The deeper question, whether intelligent life exists elsewhere in the universe, and whether it has ever sent something through our neighbourhood, is one of the most profound questions in all of science. Oumuamua does not answer it, but it did something valuable. It made the question feel immediate and real in a way that pure theoretical speculation does not. Whatever Oumuamua was, its existence reminded us that the universe is vast, and that our solar system is not sealed off from the rest of it. Things come from out there. We can see them now if they are big enough, and we are watching carefully enough. The question of what we might eventually see among those visitors is genuinely open. Here is the honest summary of where things stand. In October 2017, an object from outside our solar system was detected for the first time in recorded history. It was moving fast. It was shaped in a way nothing else in our catalogue is shaped. It came from a direction we cannot trace to any known source. It accelerated in ways that pure gravity cannot explain. It showed none of the cometary activity that should accompany such acceleration, and it was gone from observable range within 2 months of discovery. We will never see it again. It is currently somewhere beyond the orbit of Neptune, dark and cold and unreachable, moving away at a speed that will carry it clear of the solar system and back into the interstellar void forever. We have competing natural explanations for its anomalous behaviour, the most currently favoured of which involves the invisible outgassing of molecular hydrogen produced by cosmic ray irradiation of water ice over its long interstellar journey. This explanation is physically plausible and consistent with the data, but it has not been proved, and Loeb and others argue that it has problems they have detailed in the technical literature. The alien hypothesis, that Oumuamua was an artificial structure of some kind, remains a minority view in the astronomical community, held earnestly by a small number of researchers and dismissed with varying degrees of patience by most of their colleagues. The honest answer to the question of what Oumuamua was is, we don't know. And while that is unsatisfying in the way that all unresolved mysteries are unsatisfying, it is the scientifically correct answer, and it is not a failure. It is the beginning of a research program. 2 more interstellar visitors have since been confirmed. Borisov arrived in 2019, looking for all the world like a normal comet from another star system, reassuringly familiar and scientifically rich. 3I/Atlas arrived in 2025, screaming through the solar system at extraordinary speed with a chemical profile unlike anything we have seen before, hinting at an origin in the very early universe. Each visitor is different. Each one tells us that the interstellar object population is diverse, complex, and full of surprises. Each one expands what we thought we knew about the range of conditions under which planetary systems form and evolve. The Vera C. Rubin Observatory is now operational, scanning the sky with a sensitivity and cadence that will fundamentally transform how many interstellar visitors we detect. The Comet Interceptor mission is in development, building toward the moment when we can actually intercept one of these objects rather than just watch it pass. Intercept mission concepts are being studied that would allow rapid response to a new discovery. The scientific infrastructure that Oumuamua found lacking is being built, piece by piece, because of what Oumuamua revealed about our unpreparedness. In the meantime, we can hold the mystery with the kind of intellectual honesty it deserves. Something came here from another star. That sentence is remarkable. It has never been true before in the history of human scientific awareness. An object that formed around a different sun, in different circumstances, at a different time, travelled through the cold dark of interstellar space for an unknowable duration, and then happened to pass through our neighbourhood at a moment in history when we had just barely developed the tools to notice it. To truly understand why Oumuamua's arrival was significant, we need to confront some numbers about interstellar distances and how they translate to the timescales involved in what we observed. The nearest star system to our own is Alpha Centauri, a triple star system roughly 4.24 light-years away. A light-year is the distance light travels in 1 year, moving at approximately 300,000 kilometers per second. So a light-year is roughly 9.46 trillion kilometers. Multiply that by 4.24 and you get about 40 trillion kilometers. That is the distance to our nearest neighbour, which is by cosmic standards essentially next door, sitting in the same suburb of the galaxy. The actual typical distances between stars in our galaxy are considerably larger. The average separation between stars is closer to several light-years. Oumuamua's hyperbolic excess velocity, the speed at which it was moving relative to the Sun when it was still far enough away for the Sun's gravity to be negligible, was approximately 26 kilometers per second. That is fast by human standards. It equals about 93,600 kilometers per hour, fast enough to travel from New York to Los Angeles in about 16 seconds. But compared to the distances between stars, it is slow. At 26 kilometers per second, travelling the 40 trillion kilometers to Alpha Centauri would take approximately 49,000 years, which means Oumuamua had been travelling for a very, very long time before we saw it. Tracing its trajectory backward and comparing its approach direction to the positions of known nearby stars has been attempted by multiple groups, and none of them have been able to identify a convincing candidate home system. The approach direction points roughly toward the constellation Lyra, in the vicinity of the bright star Vega. But Vega is 25 light-years away, meaning Oumuamua would have needed roughly 300,000 years to travel from Vega to us. And Vega was not in the right position 300,000 years ago to have been the origin. The direction is consistent with what astronomers call the local kinematic rest frame, the average motion of all the stars in our local neighbourhood, suggesting Oumuamua was essentially at rest relative to the galactic background before our solar system swept into it. That is a statistical signature suggesting it had been drifting for an extremely long time. Some researchers have estimated that Oumuamua was probably drifting in interstellar space for between 300 million and a billion years before passing through our solar system. During all that time, it was subjected to continuous bombardment by galactic cosmic rays, high-energy particles that permeate the galaxy and slowly but relentlessly process the chemistry of any surface they strike. The radiation-processed crust that produced its reddish colour was probably built up over hundreds of millions of years. Whatever Oumuamua looked like when it left its home system, it had been significantly altered by the time we saw it. This radiation processing is one of the more underappreciated aspects of the interstellar object story. An object floating in interstellar space for hundreds of millions of years is not simply preserved in a pristine state. It is continuously modified by its environment. The outer layers of volatile ices are gradually broken down by cosmic rays. Complex organic chemistry is driven in the surface material by those same cosmic rays. Whatever volatile content the object originally had is progressively lost from the outer surface, leaving behind the processed, dark, tholin-rich crust that we observed. If Oumuamua was originally an icy comet when it left its home system, after 500 million years in interstellar space, its surface would bear little resemblance to any comet we know from our solar system. It might look, from the outside, completely inert. A dry, rocky-looking surface, with all the signs of active ice buried so far below that the warming of a single solar passage couldn't reach it in time to produce a detectable coma. This is actually one of the more physically plausible explanations for Oumuamua's lack of visible cometary activity that doesn't require invoking an unusual volatile. Maybe the outer surface simply had an insulating radiation-processed crust, thick enough to prevent volatiles from sublimating during its brief time in the inner solar system. This explanation doesn't fully account for the magnitude of the non-gravitational acceleration. An insulating crust would also suppress outgassing enough to reduce the thrust, but it at least provides a physically natural framework for why an inherently volatile-rich object might appear dry from the outside. The timescale mathematics also makes another point worth dwelling on. If Oumuamua was ejected from its home system 500 million years ago, moving at 26 kilometers per second, it has travelled roughly 13,000 light-years since leaving its birthplace, more than 10% of the diameter of the Milky Way. During that time, it passed through dozens of interstellar gas clouds, hundreds of stellar neighbourhoods, and experienced whatever the galaxy had to offer in terms of radiation, gravitational perturbations from nearby masses, and random encounters with interstellar dust and gas. It survived all of that. It arrived here more than 500 million years after it left home, and passed through our solar system in a single sweeping arc that lasted a few months from our perspective before it was gone again. That kind of timescale and distance is genuinely hard to hold in the human imagination. We are accustomed to thinking about solar system history in units of millions or billions of years, and we are accustomed to thinking about cosmic distances in units of light years. But the specific combination, a single object, travelling alone through the galaxy for hundreds of millions of years, passing through the brief warmth of our solar system, compresses the galaxy into something almost personal. This was not an abstract interstellar object. It was something specific, with a history, that happened to be in our neighbourhood for a few months and then moved on. One of the most important and least appreciated facts about the Oumuamua discovery is how exceptional the circumstances were that allowed us to find it at all. Understanding this properly requires thinking carefully about what detecting an interstellar object actually means in practice, and how many factors have to align simultaneously. First, the object has to be large enough to reflect enough light to register on a telescope. Oumuamua, at its estimated size of a few hundred meters, was near the lower limit of what pan-stars could detect. Smaller objects, things the size of a house or a building, would be completely invisible to pan-stars regardless of their trajectory. If the interstellar object population follows a typical size distribution for small bodies, more small things than large things, then pan-stars was only sampling the very largest fraction of the interstellar objects passing through the inner solar system. The total number passing through, including all the smaller objects, could be orders of magnitude larger. Second, the object has to be in the right part of the sky at the right time. Pan-stars covers about 3/4 of the sky visible from Hawaii over the course of a year, but it does not revisit every patch of sky at equal frequency. Some parts of the sky get observed more often than others, depending on the observing schedule and weather. Oumuamua happened to be in a part of the sky that Pan-STARRS was covering when it was bright enough to detect. Third, the object has to be bright enough and moving slowly enough, from Earth's perspective, that it registers as a real detection rather than as noise. Oumuamua was moving at about 6 degrees per day across the sky when it was discovered. This is fast enough to leave a visible streak in a 45-second exposure, which is what actually flagged it for human review. But an object moving even faster, closer to the Sun, or observed from a geometry that made its relative motion larger, might streak so badly across the detector that it would be automatically rejected as a cosmic ray or other artifact by the image processing software. The software has to be tuned carefully to catch fast-moving objects without being overwhelmed by false detections. Fourth, and this is particularly important, the object can only be detected after it has passed perihelion, its closest approach to the Sun, because before perihelion it is approaching from the direction of the Sun and is lost in the solar glare. Oumuamua had already passed perihelion and was heading outward when it was discovered, more than 40 days after closest approach. Those 40 days represent lost science time, a month and a half of observations that would have allowed a much richer characterization if the object had been discovered earlier. But there was no way to find it before perihelion given the geometry of the situation. Combine all of these factors, size, sky coverage, geometry, software limitations, and you get an overall detection efficiency for interstellar objects by Pan-STARRS that is probably a few % or less of the total population passing through the inner solar system. This is why the number density inferred from a single detection by Pan-STARRS implies such a surprisingly large underlying population. If we caught one in 7 years, and we only catch a few % of them when they pass, then the true passage rate is much higher than 1 per 7 years. Current best estimates suggest that the inner solar system, within about 1 astronomical unit of the Sun, is visited by roughly one 100-meter class or larger interstellar object per year, and possibly several times that depending on the true size distribution. The Vera C. Rubin Observatory changes this calculation dramatically. Its larger aperture, wider field of view, and more frequent sky coverage improve detection efficiency by perhaps a factor of 10 to 100 over Pan-STARRS. More importantly, it revisits each patch of sky every few nights rather than every few weeks, which means it can track fast-moving objects more reliably and can begin to detect them while they are still on the inbound leg of their trajectory, before perihelion rather than after. For future interstellar visitors, this early detection will be transformative. Instead of 2 months of observations, we might have 6 months to a year. Instead of scrambling to point every available telescope at a fading object, we can mount a systematic, coordinated multi-wavelength campaign. The science return from a well-prepared observation program of an interstellar object would dwarf what we learned from Oumuamua. There is also the possibility of spacecraft rendezvous becoming realistic for at least some future visitors. Any interstellar object discovered while it is still months from perihelion gives mission planners time to identify whether a rapid response spacecraft launch could intercept it. The velocities involved are still challenging. Catching up with something moving at 20+ kilometers per second relative to the Sun requires either catching it near perihelion when it's closest, or launching a spacecraft with enough speed to chase it down over a long baseline. But for objects discovered early enough with favourable trajectories, mission concepts using conventional chemical propulsion with a Jupiter gravity assist could potentially enable an intercept. The strategic logic for developing rapid response interstellar object intercept capability is straightforward. We have had 3 interstellar visitors in 8 years. The next one could arrive any time. With the Rubin Observatory now operational, we will likely know about the next major interstellar visitor months before it reaches perihelion. If we have a spacecraft already built and ready, sitting in storage, waiting for a target, the lead time from discovery to launch decision could be measured in weeks rather than years. This is the rationale behind the Comet Interceptor mission and similar proposals. The cost of building and launching such a spacecraft is modest compared to the scientific return of a close encounter with an interstellar visitor. We will never know with certainty what Oumuamua actually looked like. But we can reason from what we do know, informed by what we know about similar objects in our own solar system, to construct a picture of what a spacecraft rendezvous might have found. If Oumuamua was indeed a comet-like body, a water ice-rich object with a radiation-processed surface, then its surface would have borne a strong resemblance to the nuclei of comets we have visited with spacecraft. The Rosetta mission's encounter with Comet 67P/Churyumov-Gerasimenko is our most detailed close-up look at a cometary nucleus, and it revealed a deeply strange, dramatically irregular landscape. Cliffs of hard, dark material, deep pits whose origin is still debated, bizarre smooth regions alongside heavily fractured and eroded terrain, a surface almost perfectly black, darker than coal, with an albedo of only about 6%, made up of the same kind of tholin-rich, radiation-processed organic crust that Oumuamua's reddish colour suggested. Oumuamua, if compositionally similar, might have had a surface with some of the same features. A dark, irregular landscape. Layered structures from the slow accumulation of surface deposits, perhaps evidence of internal stress fractures from the tidal forces experienced during a close encounter with some massive body at some point in its history. The colour mottling that comets show, patches of slightly different colour and reflectivity corresponding to different surface chemistry, might have been present. If Oumuamua were the pancake shape rather than the cigar, a spacecraft approaching from above would have seen something like a large, relatively flat, irregular slab, tumbling lazily in space, with its dark surface absorbing and radiating the sun's warmth. Its thin profile would have made it an eerie thing to approach, appearing from a distance as a point, then gradually resolving into a coin-like shape, growing wider relative to its depth until you were close enough to see its texture and detail. If instead it were the cigar shape, the approach would have been along its length, the object growing from a point into a needle and then gradually resolving into a long, irregular cylinder as you came close enough to see its surface. Either way, the scientific instruments on a hypothetical rendezvous spacecraft would have told us things that no amount of Earth-based observation could reveal. A mass spectrometer sniffing the thin gaseous envelope around the object would have immediately identified the molecules being outgassed, if any, and measured their isotopic ratios with high precision. An imaging system would have resolved surface features down to centimetre scales. A thermal camera would have mapped the temperature distribution across the surface, identifying active warm spots where sublimation might be occurring. A radar system could have probed the interior structure, revealing whether the object was solid throughout or had an internal structure with layers or voids. These measurements would have, in all likelihood, definitively settled the mystery. If the mass spectrometer found molecular hydrogen in the thin gas cloud around the object, consistent with the Bergner-Seligman model, that would be strong confirmation of the natural outgassing hypothesis. If it found nothing, no gas at all, that would push back toward either a truly inert rocky body or something more exotic. If the thermal imaging found an extremely low thermal inertia, meaning the surface temperature changed rapidly with changing illumination, that would suggest a loose, porous surface, possibly a very fluffy aggregate structure rather than solid rock or ice. If the radar found a hollow interior or a layered structure, that would open entirely new questions about how the object formed. The tragedy of missing Oumuamua, and it does feel like a tragedy in the scientific sense, is that it was genuinely answerable. The mystery of what Oumuamua was is not an unanswerable question like what caused the Big Bang. It is a question that a piece of hardware with the right instruments, in the right place at the right time, could have resolved definitively. We just didn't have that hardware ready. The preparation for the next visitor is, among other things, a commitment to not repeating that particular failure. When Oumuamua was travelling through interstellar space, through the vast regions between star systems where the density of matter drops to almost nothing, it was not entirely alone. The interstellar medium, the diffuse collection of gas and dust that fills the space between stars, is thin by any measure relevant to human experience. In the most rarefied regions of interstellar space, there might be one hydrogen atom per cubic centimetre. For comparison, sea-level air on Earth contains about 10 billion molecules per cubic centimetre. Interstellar space is, for practical purposes, a harder vacuum than anything achievable in a laboratory on Earth. And yet, thin as it is, the interstellar medium is not nothing. It has structure, temperature, magnetic fields, and chemical complexity. Over millions of years, even the slow drift through this thin medium leaves marks. Interstellar dust grains, tiny particles of silicate and carbon compounds, much smaller than a grain of sand, impact the surface of Oumuamua at cosmic velocities, slowly eroding and modifying the surface over time. Interstellar gas pressure, though negligibly small in absolute terms, subtly influences the trajectory of any object with a high enough surface area to mass ratio, and the interstellar radiation field, the diffuse bath of photons from millions of stars throughout the galaxy, provides a steady energy input that contributes to the surface chemistry. The cosmic ray bombardment is particularly significant. Cosmic rays are not rays in the optical sense. They are high-energy subatomic particles, mostly protons, accelerated to relativistic speeds by supernova shocks and other energetic processes in the galaxy. They permeate the interstellar medium and penetrate into the surfaces of small bodies, depositing energy that drives chemical reactions in the subsurface material. In ice-rich bodies, this produces the complex organic molecules called tholins that give outer solar system objects their characteristic reddish color. In water ice, as Bergner's work highlights, it also produces trapped molecular hydrogen. In rocky material, it can cause structural changes in the crystal lattice of minerals. All of this means that an interstellar object is not a static, preserved artifact. It is a dynamically evolving system, continuously being acted upon by its environment. What we observed when Oumuamua briefly entered our observable range was not Oumuamua, as it was when it left its home system, possibly 500 million years ago. It was Oumuamua after 500 million years of interstellar processing. Reading its properties backward in time to infer its original state is a deconvolution problem. You have to understand all the modifications that occurred during the journey to know what you started with. This makes interpretation difficult, but it also makes interstellar objects interesting in a new way. They're not just messengers carrying the signal of their origin. They are messengers that have been modified by everything they pass through on the way. The processing history, encoded in their surface chemistry, is, in principle, a record of the interstellar environments they travelled through. An object that spent 100 million years drifting through a dense molecular cloud would look different from one that spent the same time in the diffuse warm interstellar medium. Reading those differences requires knowing what to look for, and that knowledge is still being built. When we get a sample from an interstellar object, when some future spacecraft returns a piece of 3I/Atlas or its successor to Earth, laboratory analysis of that sample will provide a level of detail that no remote observation can match. Isotopic ratios measured with mass spectrometry at the precision achievable in Earth-based laboratories are far beyond what any spacecraft mass spectrometer can provide. Mineralogical analysis of crystal structures under an electron microscope can reveal formation and processing conditions with extraordinary precision. The organic chemistry measurable by NMR spectroscopy or other techniques would provide a detailed inventory of the complex molecules produced by interstellar chemistry over millions of years. These are the analyses that will eventually tell us not just what interstellar objects are, but where they came from, how they got here, and what the galaxy has been doing with planetary debris for the last several billion years. Oumuamua was the announcement that these analyses were possible in principle. 3I/Atlas was the demonstration that we could study interstellar objects systematically. The sample return mission will be the chapter that comes after that. One of the most profound shifts in how astronomers think about the solar system that emerged from the Oumuamua discovery is the shift from thinking of the solar system as an isolated island to thinking of it as part of a connected galactic ecosystem. This is not a metaphor, it is a genuine change in the physical picture of what our solar system is and how it relates to the rest of the Milky Way. Before 2017, the standard picture of the solar system was roughly this: a central star orbited by planets and their moons, surrounded by an asteroid belt, further surrounded by the Kuiper belt and the distant Oort cloud. The Oort cloud, a vast spherical reservoir of loosely bound comets extending perhaps a quarter of the way to the nearest star, was considered the outermost boundary of the solar system. Beyond it, interstellar space. The two were separate realms, and the traffic between them, while acknowledged theoretically, was never actually observed. What Oumuamua demonstrated is that this boundary is far more porous than the textbook picture suggested. Not only do objects cross it, they cross it regularly enough that a single telescope operating for 7 years could catch one, and if one was detected under the specific observational conditions that applied in 2017, many more must have been passing through unseen in every previous decade of human history. Going further back, in the billions of years since the solar system formed, an incomprehensible number of interstellar objects have passed through the inner solar system. Some may have been captured into bound orbits by gravitational interactions with the outer planets. Some may have contributed material to the early Earth during the heavy bombardment period 4 billion years ago. Some may carry chemical signals from the earliest epochs of cosmic history, as 3I/Atlas apparently does. The picture this creates is of a solar system that is constantly being interpenetrated by material from the rest of the galaxy, slowly exchanging chemistry with the wider interstellar medium over geological timescales. This is not just of academic interest. It has potential implications for the origin of life on Earth. The hypothesis of lithopanspermia, the transport of life or prebiotic chemistry through space via rocks, has traditionally been discussed in the context of exchange between planets within a single solar system, Mars and Earth for example. But if interstellar objects are common, and if some of them originate in systems where life has or had existed, then interstellar panspermia becomes a physically plausible mechanism in a way it was not when interstellar objects were purely hypothetical. To be clear, we have no evidence for interstellar panspermia. The barriers to microbial survival of interstellar transit are formidable. Extreme cold, intense cosmic radiation, bombardment over millions of years, and the trauma of planetary ejection and final atmospheric entry in a destination system are all severe challenges. The scientific consensus is that these barriers are probably insurmountable, at least for familiar carbon-based life. But the probability arguments are substantially different when you're talking about millions of interstellar transits over billions of years versus a handful of rare events. Low probability events happen when you have enough trials. Interstellar objects also carry chemical and physical information about the range of planetary systems in the galaxy in a way that exoplanet observations cannot. When we detect an exoplanet through the transit method, the dimming of its host star as the planet passes in front, we learn about the planet's size and orbital period. With additional observations using radial velocity and transmission spectroscopy, we might learn something about the planet's mass and the broad composition of its atmosphere. But we cannot access the planet's surface, its mineralogy, its detailed organic chemistry, its isotopic composition. These are things that would require a sample return mission, and no sample return mission to another solar system is remotely possible with foreseeable technology. Interstellar objects offer a workaround. They are, in a very real sense, samples from other planetary systems that have delivered themselves to our doorstep. When we eventually retrieve a sample from an interstellar object and analyze it in an Earth-based laboratory, we will be holding, literally in our hands, a piece of a world that formed around another star. The mineralogy of that piece will tell us about the temperatures and pressures under which it formed. The organic chemistry will tell us about the availability of carbon-bearing compounds in its home disk. The isotopic ratios will date its formation and reveal the nucleosynthetic history of the stellar material from which its host system formed. This is information about planetary system formation across the galaxy that cannot be obtained in any other way. Consider what isotopic analysis of solar system materials has already told us about our own solar system's history. The ratios of different oxygen isotopes in different types of meteorites have been used to trace the mixing of material from different regions of the solar nebula during the solar system's formation. The ratios of certain short-lived radioactive isotopes preserved in ancient meteorites have provided dates for early solar system events with a precision of a few 100,000 years out of a total age of 4.56 billion years. The isotopic composition of presolar grains, tiny mineral grains within meteorites that predate the formation of our solar system, preserved from the stellar environments where they formed, has allowed astronomers to identify the types of stars that contributed material to our solar system's birth cloud. All of this extraordinary detail comes from the analysis of materials that travelled far shorter distances under far less hostile conditions than an interstellar object must endure. The materials in interstellar objects have been subjected to more extreme radiation processing, more extreme thermal cycling, from deep cold to near solar temperatures and back, and longer transit times than anything in our meteorite collection. But those extremes also mean that the interstellar objects carry information about a wider range of environments and a longer span of cosmic history than anything we have so far been able to directly analyze. 3I/Atlas, with its apparent indication of formation in the very early universe, represents the extreme end of this possibility. If its isotopic signature is confirmed to be consistent with an age of 10 billion years or more, formed before our Sun existed in one of the first stellar generations, then holding a sample of 3I/Atlas would be the closest thing to holding a piece of the young universe that human hands could achieve. It would be a genuine relic of a cosmic epoch, otherwise accessible only through the faint light of very distant galaxies. No telescope can show us the surface mineralogy of a 10-billion-year-old world. But an interstellar comet born in that world can carry a sample of that mineralogy to our laboratories. This is why the discovery of interstellar objects matters beyond the immediate scientific puzzles they present. Each one is a message from somewhere else in the galaxy and sometime else in cosmic history. Oumuamua was the first message we recognized. It was garbled. We couldn't fully decode it before it was gone. Borisov was the second, clearer in some ways, raising new questions of its own. 3I/Atlas was the third, apparently bearing the most ancient and exotic chemistry of all, and the Rubin Observatory is about to give us dozens more. We are at the very beginning of reading these messages. The alphabet is being assembled. The grammar is starting to become clear. The content, as it accumulates over the next decade, will reshape our understanding of the galaxy in ways that are genuinely hard to predict. That is the best kind of science. The kind that opens a new window onto the universe and lets you see things you had not previously known were there. Oumuamua was a messenger from afar arriving first, just as its Hawaiian name said, and it arrived precisely when humanity had just barely developed the ability to notice it. The timing, in a universe 13.8 billion years old, is either an extraordinary coincidence or a reflection of the fact that detection capability and the arrival of visitors are not independent. We could only find Oumuamua once we built pan-stars, and we built pan-stars because we were systematically improving our ability to watch the sky. The universe sends these messengers constantly. We are only now learning to read them. There is a dimension of the Oumuamua story that has nothing to do with the object's physical properties and everything to do with what it did to the practice of astronomy as a human enterprise. The discovery did not just expand our knowledge of what exists in space. It reorganized the scientific community, reshaped research priorities, catalyzed new funding streams, and forced a reckoning with the culture and values of professional astronomy in ways that will continue unfolding for a generation. The most immediate consequence was the emergence of interstellar object science as a recognized subfield. Before October 2017, the study of interstellar objects was a theoretical exercise. Papers had been written predicting their existence and estimating their properties, but there was no community of researchers whose careers were organized around studying them, no dedicated sessions at major conferences, no review articles, no textbook chapters. Oumuamua changed all of that within months. By early 2018, a formal international collaboration called the Oumuamua ISSI Team, ISSI standing for International Space Science Institute, had been formed, bringing together dozens of researchers across disciplines to synthesize the available observations and develop theoretical frameworks. The team's published review in 2019 became an instant reference in the new field. Conference sessions on interstellar objects appeared at every major planetary science and astronomy meeting within a year of the discovery. Grant applications explicitly focused on interstellar object science began appearing at funding agencies. Graduate students began choosing thesis projects involving this new category of object. The scientific ecosystem of a new field assembled itself with remarkable speed, driven by the urgency of the discovery and the recognition that more objects would be coming. The competition between natural and artificial explanations also had an unusual sociological effect. It brought in researchers from outside the traditional planetary science community. Physicists, chemists, and astrobiologists who had not previously worked on small solar system bodies suddenly had a reason to engage with the interstellar object problem. The alien hypothesis, whatever its scientific merits, served as an attention-generating machine that brought new eyes to the dataset and new questions to the discourse. Some of those new eyes found genuine insights. The hydrogen from irradiated water model, for example, came partly from Bergner's background in astrochemistry rather than planetary science. This is a general truth about science. Controversies, even ones that ultimately resolve in favor of the mundane, accelerate progress. The debate over Oumuamua's nature motivated more careful analysis of the data, more creative hypothesis generation, and more rapid development of detection infrastructure than might have occurred if the object had been unambiguously identified as a boring rock from another star system. The alien hypothesis, by raising the stakes and drawing public attention, effectively subsidized the planetary science through increased media interest, public engagement, and the soft social pressure on funding agencies to support research that the public cared about. This dynamic is worth noting because it will repeat. Every future interstellar visitor that has anomalous properties will prompt a similar debate. The field is now building the cultural and institutional infrastructure to handle that debate productively, to engage seriously with exotic hypotheses without being paralyzed by them, to maintain scientific rigor without dismissing ideas simply because they are unusual, and to communicate uncertainty honestly to the public without either overselling or underselling what is known. These are genuinely difficult balancing acts, and Oumuamua was the training ground where the astronomical community first learned to attempt them. The broader public's engagement with the Oumuamua story also revealed something important about science communication. The alien hypothesis generated headlines. The natural explanations generated much less coverage. This is the standard media dynamic. Exotic claims attract attention. Careful scientific revision attracts much less. But the Oumuamua story demonstrated that the public genuinely cares about this kind of question. Readership numbers, search trends, and engagement metrics for Oumuamua-related content were exceptional, suggesting a level of public interest in the question of whether we are alone in the universe that is both deep and broadly distributed across demographics. Tapping into that interest while maintaining scientific integrity is one of the central challenges of contemporary science communication. The Oumuamua story also demonstrated that scientists, when they explain their uncertainty honestly and present the competing hypotheses clearly without prematurely closing them, can maintain public engagement even in the absence of a definitive resolution. The story of "we don't know yet and here's why it's complicated" turned out to be more sustainably interesting than either "it's definitely alien" or "it's definitely not alien." The not knowing is genuinely interesting when the stakes are high enough and the explanation is given enough depth. That is part of what this channel exists to do, to sit with the uncertainty, explain the depth of the problem, and trust that the audience is sophisticated enough to find the not knowing as compelling as any definitive answer. Because sometimes the not knowing is where the science actually lives, and Oumuamua is living proof. The universe is 13.8 billion years old, vast beyond any number that fits comfortably in the human mind, and it has been sending objects like Oumuamua through our neighbourhood since long before the Earth existed. For the first time in all of that history, we had the eyes to see one. The fact that we barely caught it, the fact that it raised more questions than it answered, the fact that we still don't know exactly what it was. None of that diminishes what happened. It makes it more real. Science is not a collection of finished answers. It is a collection of increasingly precise questions, and the question that Oumuamua asked, the one that still sits unanswered at the heart of this whole extraordinary story, is one of the most precise and most profound that the cosmos has ever posed to us. What is out there, drifting between the stars, and when will we finally learn to read what it is carrying? The scientific tools being built right now, the Rubin Observatory cataloguing millions of solar system objects and catching interstellar visitors as they arrive, the Comet Interceptor waiting patiently for a target, the next generation of spacecraft mission concepts that could chase these objects at speeds never before attempted, are the infrastructure of an answer. They are being built because of what Oumuamua revealed about our ignorance and what that ignorance implied about what there is still left to discover. In a field defined by the discovery of things we didn't know were there, planets around other stars, the accelerating expansion of the universe, gravitational waves rippling through space-time, interstellar objects represent one of the most recently opened and most richly promising frontiers. The era of finding them one at a time, by lucky chance and barely adequate, instruments, is ending. The era of systematic study, of population statistics and comparative planetology across stellar systems, is beginning. Oumuamua, strange, elusive, insufficiently observed, and never explained to everyone's satisfaction, will be remembered as the object that started all of it. The first scout, as its name said from the beginning, the first messenger from the universe beyond, arriving first, reaching out across the incomprehensible distances of interstellar space to touch our instruments for 2 brief months before vanishing forever. So, that's it for now. See you later, guys.